Hello everyone. In this video, I'm gonna put a few more examples on U-substitution. The first example I like to take is the integral of cotangent of x dx, which is really similar to the integral of tangent of x dx that we did in class. So I'm gonna break it into very similar work. Cotangent of x is cosine of x over sine of x. So the integral is integral of cos x over sine x dx. And we will take this as our u. If I let u equal sine of x, then the derivative is cos x. So du becomes cos x dx, which will work out nicely. Okay, so I'm going to let u equal sine x. Then du will be cosine of x dx, which means that dx equals du over cos x. So I will put this in for dx, and I will put this in for u in the substitution. Okay? So this expression now equals the integral of cosine of x divided by u, that's what sine x is, and dx becomes du over cos x. So the cosine x cancels. This will give you integral of 1 over u du, or the integral of 1 over u is natural log of u plus c, which gives you natural log of sine of x plus c. Now, to make it similar to the integral of tangent of x that we studied, I will change sine x to 1 over sec x. So if I do 1 over sec x in here, then this produces a minus of natural log of sec x plus c. This is just your algebra, one of the log rules that we learned. Okay? So the integral of cotangent of x dx is negative natural log of secant of x plus c. Okay, I am going to box that because we need to memorize this formula. Let's see. This is one of the formulas that I asked you to memorize. The next example I want to do is the integral of one of those tricky functions, the secant function. Okay? So the next example is integral of secant of x dx. This is a very tricky integral. It doesn't come naturally. So the trick here is to multiply secant of x by sec x plus tan x divided by sec x plus tan x. You'll see why this trick works in a minute, but I've just divided it by 1. It's just cleverly written 1, sec x plus tan x over sec x plus tan x. So if I multiply the top through, I get secant squared x plus secant of x times tangent x divided by secant x plus tangent x dx. Now, you can see that the derivative of secant x is sec x tan x, and the derivative of tangent x being sec squared x. You can see that the derivative of the denominator here is exactly what we have in the numerator. Just like what we had here, the derivative of sine x is cos x, so u equals sine x worked nicely. Okay, similarly here, the derivative of sec x plus tan x is sec squared x plus sec x tan x. So I'm going to let u equal equal secant of x plus tangent of x, then du equals the derivative of sec x is sec x tan x, and derivative of tan x is sec squared x. So du is sec x tan x plus sec squared x dx. So solving for dx, this gives me du over sec x tan x plus sec squared x. Okay, sec squared x. So I'm going to stick this in for dx and u in for sec x plus tan x in this expression. Okay, so this now equals the integral of sec squared x plus sec x tan x. I'm looking at that one. Okay, so the top is sec squared x over sec x tan x. The bottom is u, which is that one. Okay, times dx now is du over sec x tan x plus secant squared x. Now you can see that this expression is the same as that expression. They cancel out, and that gives us integral of 1 over u du, which equals natural log of absolute value of u plus c, which equals natural log of absolute value of secant of x plus tangent of x plus c. So the integral of sec x dx equals the integral of natural log of sec x plus tan x plus c. This is the other example, expression that I gave you in class to study, to memorize. Okay, a similar work can be done for cosec x. Okay, I'll just leave that for you to try. But this is one thing I want to say. So this particular tricky substitution only work for this kind of problem for sec x or cosec x. I haven't seen it done on different problems. So just memorize these formulas, and that's more important because they show up a lot. These expressions show up in the trig integrals and trig substitution problems. The next example I want to consider is the integral of x squared times 1 plus 2x cubed to the power of 5 dx. I will let u equal 1 plus 2x cubed. You can see that that's the inside expression, nicely put, and its derivative is not exactly x squared, but it is 6 times x squared, so it works really well. So u equals 1 plus 2x cubed, then du becomes 6x squared dx, or dx is du over 6x squared. So that would be the expression I will put in place of dx. So this being a definite integral, we will have to calculate the values of u at 0 and at 1. So u evaluated at 0 is 1 plus 2 times 0 cubed, which is 1 plus 0, which is 1. This 0 cubed is 0. And u evaluated at 1, I'm looking at these expressions here, at these numbers. So u evaluated at 1 is 1 plus 2 times 1 cubed. 1 cubed is 1, so 1 plus 2 times 1 cubed is 1 plus 2, which equals 3. So this expression now, this integral is now the integral from 1 to 3 of x cubed times u to the power of 5 times du over 6x squared, not x cubed, x squared times u to the 5th. Du over x squared is the expression dx. Cancel x squared. That gives you 1 over 6 times the integral of u to the 5th du from 1 to 3. Well, integral of u to the 5th is 1/6 u to the power of 6 evaluated from 1 to 3. Or this is just 1 over 36 times u to the power of 6 evaluated from 1 to 3. So I'm going to put 3 in, and I'm going to put 1 in. This gives me 1 over 36 times 3 to the 6th minus 1 over 36 times 1 to the 6th. Or just 1 over 36 times 3 to the 6th minus 1 to the 6th. Well, 3 to the 6th is actually 729. Okay, and 1 to the 6th is just 1. So subtract 1 gives you 728 over 36. You can see 728 is divisible by 4, so is 36. So if you reduce that, this will give you 182 over 9, and that's the final answer. Okay, so the purpose of this example is just to remind you, to give you one more example of this definite integral. Okay, when you have a definite integral, evaluate the u values, put the u values, corresponding u values on the limits, and you don't have to get back to x's, just evaluate the values at those u values, like the limits. This example, I just want you to try it at home before I look at it on Thursday. Okay, I want you to try it at home. It is a little bit tricky, but it's kind of like a challenge. I want you to challenge yourself to try it, and then I'll give you the integral on Thursday. Okay, the next example is a kind of nice, easy example, the integral of sine of 2x dx. For this one, I'm going to let u equal 2x. Derivative of u is just 2, so du will be just dx times 2. So it's going to work out nicely because 2 is just a constant. So I'm going to take the derivative of u, it's 2 dx. So solve for dx, that will be du over 2. Now this integral equals sine of u, that's 2x is u, dx is du over 2. Or just 1/2 times the integral of sine of u du. Well, remember the integral of sine of u is minus cosine of u, so this gives you 1/2 times minus cosine of u plus c, or minus 1/2 cosine of 2x plus c. That's a nice little example. Well, why did I bring this example here? This could have been example 1 or 2. It's just kind of easy problem. Well, here's the point. Well, if you look at this problem, this 2, there's nothing special about that number 2. It could have been 5, for example. What would happen if I have sine of 5x? Well, I would let u be 5x, and then I'll have this 5 and a 5 and a 5. Instead of a cosine of 1 over 2, I would have 1 over 5. All right, so, well, so if I want to get the integral of sine of 5x, That's just simply 1 over 5 cosine of 5x plus c. Or if it is sine of 20x, I have 1 over 20 cos 20x, with a minus, of course, because the integral of sine x is minus cos x. Well, there's nothing special about the sine function here. It could have been the cosine function, or e to the power of. It's just that we need to know the integral of that function exactly. If we know that integral of that function, this process, we could mimic this process very easily. In other words, let me clean this up. Say I have integral of cosine of 20x dx. Well, knowing the integral of cosine of u is just sine of u, I would just have 1 over 20 sine of 20x plus c. Okay? Or the integral of e to the power of, I don't know, 100x. Knowing the integral of e to the u is just e to the u, I would have e to the power of 100 would produce 1 over 100 e to the power of 100x plus c. Okay? If you know the integral of a function, then a constant multiple of x will only produce 1 over the constant in front of it. So if I have secant squared of pi x, that's the constant pi. So I know it produces 1 over pi. All I have to remember is what is the integral of secant squared of u? Well, that would be tangent of u. Okay, you don't have to do the u substitution in cases like this. You can just put this in. I will accept it in exams or quizzes. If you just know what, remember that it produces 1 over the constant, and keep the constant along with x, then the integral will work out nicely. So if I have secant of 5x times tangent of 5x dx, this is more like a 5x in place of x of secant of u tangent of u kind of problem. Integral of secant u tan u is secant of u, so I have 1 over 5 secant of 5x plus c would be the integral. So the purpose of this example is just to show you more like a formula, a shortcut to integral of a constant multiple of x. If it's something else multiple of x, it does not work. But if it's a constant multiple of x, then 1 over the constant sits out in front, and then that constant multiple of x follows. All right. So this is the examples I wanted to look at for the u substitution. I will be doing the second video on a different topic.